Classification of matter. How can you tell if a substance is pure or a mixture? Let's review a few of the concepts from earlier this week. Matter is what we study in chemistry, its behavior and how it changes. We define matter as anything that has mass and takes up space. We can also rewrite the word space as volume. Anything that has mass and volume. We will focus on 3 states of matter throughout this unit: solid, liquid, and gaseous states. Ensure that you review the table you copied earlier this week with properties of each of these individual states. Why do different states of matter exist? Well, it's all about the collisions between particles. We'll talk about collisions a little bit further in depth as we move throughout the year, but here's a difference between collisions and your states of matter. Solid molecules are very close together, very neatly packed. The particles are simply vibrating back and forth. There are absolutely no collisions between solid particles. Liquid molecules, on the other hand, are a little bit more free. They flow or roll, if you remember from earlier this week. They can move one right past another. As a result, there are some collisions, but still not very many. And last but not least, the gaseous state of matter. Gas molecules move in rapid, random motion. They expand to fill whatever container they're in, and as a result, they have many, many collisions between themselves and the walls of their container. An element is the simplest form of matter that has only one type of atom and cannot be broken down further. Now, in all actuality, I can take one of these elements. Let's take nitrogen, for example, here, element number 7. Nitrogen is made up of only one type of atom. Those atoms have 7 protons, 7 electrons, and their number of neutrons can vary. But if I take a nitrogen atom, and if I break it down into those subatomic particles, those protons, electrons, and neutrons, it no longer retains the same properties. It differs. So element is the simplest form of matter that has only one type of atom. I can't break it down any further. Compound, 2 or more different elements that are chemically combined. We talked about that earlier this week, and we're going to add to this definition today that they can only be separated by chemical means. So what exactly does that mean? That means that a chemical reaction must occur in order to break apart these different elements in a compound. So I need energy to break this bond between the hydrogen and oxygen and this bond between the hydrogen and oxygen. Because I need a chemical reaction to do that, I know that this is a compound. I can't just physically come in and with my fingers take this hydrogen and pluck it off. If I did, that means I have special powers. Because I need a chemical reaction in order to separate them, it is a compound. Same over here on the left. This is what we call an ionic compound, and you'll learn more about these a little bit later. But in order to separate these yellow spheres from the red spheres, I need a chemical reaction. I need energy to come in and break these bonds, and then I form new bonds as I rearrange them on the other side of that chemical reaction. So remember, I have reactants on the left. They form products over here on the right. All we've done is rearrange that matter, but in the reactant side, we break bonds, and in the product side, we form new bonds. So here comes the good stuff. The goal of this lesson is for you to be able to differentiate between pure substances and mixtures. So write down the definition of pure substance. Only one type of matter can only be separated by chemical means. An example of chemical means is electrolysis. We use electricity. There's electro, or the word electro. We use electricity and lysis. I know you came from biology last year. Lysis means to break apart. So we use energy to break bonds. Pure substance, only one type of matter. What were those types of matter again? Elements, compounds, and molecules. I can only separate compounds and molecules by chemical means. An element can't be separated any further, so I know if I have just a pure element, it has to be a pure substance. If you didn't write them down on the previous slide, I want you to write them down now. Examples of pure substances are elements, which are composed of identical atoms. Any metal is going to be a perfect example of a pure substance. Something like this copper wire or this aluminum foil is a pure substance, only one type of identical atom. The second example of a pure substance is a compound. Remember, a compound is two or more different elements that are chemically combined. They are combined in a fixed ratio, meaning that the number of one element to the other is always the same. So for water, there are always 2 hydrogen for every 1 oxygen. And carbon dioxide, there's always 1 carbon for every 2 oxygen. So that's what we mean by fixed ratio, these numbers here. And if you don't see a number, it's actually the number 1. The properties differ from those of individual elements. So the properties of water are very different than the properties of just hydrogen alone or just oxygen alone. Same thing here. The properties of carbon dioxide are very different than the properties of carbon on its own and oxygen on its own. An example of a compound is sodium chloride. Essentially, I can take pretty much any 2 elements off the periodic table, and if I chemically combine them, I've made a compound. Compounds also can be made up of more than 2 elements. I can have something like NH4, NO3, ammonium nitrate, and this is still a compound. I have 2 or more elements. In this case, I have nitrogen, hydrogen, and oxygen, 3 different elements. They're chemically combined in a fixed ratio, and the properties of the individual elements are different than those of the entire thing as a whole. To elaborate a little bit on pure substances, I want you to copy down the following laws. The law of definite composition. Composition meaning what something is made up of. The law of definite composition says that a given compound, remember compound, 2 or more different elements chemically combined, a given compound always contains the same fixed ratio of elements. So a given compound, let's say methane, the chemical formula for methane is CH4. This compound, CH4, always contains 1 carbon for every 4 hydrogen, every single time. Its chemical formula is always CH4. We call that a fixed ratio. Just like we said on the previous slide for water, it's a compound, H2O. It's a fixed ratio of 2 hydrogen to that 1 oxygen. Law number 2, the law of multiple proportions. Elements can combine in different whole number ratios to form different compounds. So if we continue using methane as our example, methane was CH4, 1 carbon for every 4 hydrogen. There's also a substance, C2H6, called ethene. Another whole number ratio. This time I have 2 carbon for every 6 hydrogen, and I have formed a different compound. This compound, C2H6, has very different properties than methane, CH4. Same elements, carbon and hydrogen, but different ratios of one element to another. Law of multiple proportions. Here's another example. I have 2 different compounds here. In the first, I have carbon monoxide, 1 carbon for every 1 oxygen. But I can also have 1 carbon for every 2 oxygen. So I have 2 different compounds, carbon monoxide and carbon dioxide. These compounds have definite compositions. Carbon monoxide is always a 1-to-1 ratio of carbon to oxygen. Carbon dioxide is always a definite ratio of 1 carbon to 2 oxygen. However, I have multiple proportions. I have the same elements but in different whole number ratios. Next, we have mixture. 2 or more compounds physically blended together and can be separated by physical means. So we said a pure substance is only one type of matter. A mixture is 2 or more types of matter. And our key word here is that they are physically blended together and they can be separated by physical means. Take a moment, think about what we said earlier this week were physical changes. Changes in between states of matter, solid, liquid, gas. So think of those processes, evaporation, melting, freezing, etc. Or changing the physical shape, tearing, ripping, grinding, churning, etc. If I can physically separate 2 or more compounds one from another, I have a mixture. There are 2 types of mixtures: homogeneous, one phase looks the same throughout. Heterogeneous, different phases, I can see different parts. Let's recall from our genetics unit in biology last year what these words meant: homogeneous and heterogeneous, or homozygous and heterozygous. Homozygous meant that the alleles for a certain trait were the same, so 2 capital letters or 2 lowercase letters. Whereas heterogeneous meant that the alleles for a trait were different, so 1 capital, 1 lowercase. Well, we're going to use that concept from last year to help us remember the difference between our types of mixtures. And a homogeneous mixture, they're all one phase, meaning that the 2 different compounds that are physically blended, they're either both liquids, both solids, or both gases. And a heterogeneous mixture, my 2 compounds are in different phases. One might be a liquid and the other might be a solid. Or one might be a liquid and the other might be a gas, like say dissolved oxygen in ocean water. That would be a heterogeneous mixture. Colloid suspensions and emulsions are all examples of heterogeneous liquids. Take a moment to write these down and I will give you descriptions in the following slides. A colloid is when one substance is dispersed as very fine particles in another substance. The easiest example of a colloid is fog. Fog is water vapor, as you can see there, that's dispersed as very fine particles in air. Paint is very fine particles of color dispersed throughout the white paint. Colloids are heterogeneous because I have 2 different phases. In this soap, the bubbles of air are the fine particles that are dispersed throughout the liquid water. I have 2 different phases. One is the liquid phase, the water, and the other is the gaseous phase, as those air particles are trapped as bubbles inside of the liquid. Another example of a heterogeneous mixture is a suspension, a mixture from which some of the particles settle out slowly upon standing. If you think about a glass of orange juice, if you pour yourself a glass in the morning, the very first thing you do when you take that carton or the jug of orange juice out is give it a good shake. We give it a good shake because at the very bottom of the container is where all the good stuff is. If you're like me, you like orange juice that has little bits of orange in it, and those little bits settle out at the bottom of the container, as well as the sugars and anything else that they add. So in a suspension, what we want to do while we shake the container is we suspend those delicious particles that are sitting there at the bottom of the juice container throughout the entire drink or throughout the entire container. The last type of heterogeneous mixtures is called emulsions. An emulsion is a colloidal dispersion of one liquid and another. So to have 2 liquids that are mixed or suspended one in another, we have to have liquids that wouldn't typically mix one with another, like oil and water. A classic example of an emulsion is mayonnaise. Mayonnaise is a mixture of oil, egg yolks, lemon, and vinegar. In order to get that consistency of the mayonnaise, you slowly add the oil and the egg yolk, and you rapidly mix that egg yolk, kind of whipping it up in order to suspend and mix those liquid molecules that wouldn't typically mix on their own. So here comes the fun stuff. A pure substance is only one type of matter, whereas a mixture is two or more types of matter that are physically blended or combined. Well, how do we figure out what type of matter we have? It all has to do with testing that substance and determining how can I separate it. Can I separate it physically, or do I have to separate it chemically? The first step is to observe your sample of matter. Does it look like it's one type of matter, or does it look like it's more than one type of matter? Once you've answered that question, the next question is, how can I separate that type of matter? Do I separate it physically, or can I separate it physically, or do I have to separate it chemically? And the only way to do that is to test it out. Following are a few different types of separation techniques. Make sure you've written them all down with a good definition or description of what that technique entails, and understand if it's a physical separation or a chemical separation. The first technique is filtration. You've probably done this at some point, maybe not in the chemistry classroom, but just at some point throughout your life, you've probably filtered one substance from another. In filtration, solid substances are separated from liquids and solutions. So on your paper for filtration, the most important thing that you need to know is that you are separating solid from liquid or solutions. The equipment that you're going to use is going to be a funnel and filter paper. So if you take a look at the picture here, in this, it looks like an Erlenmeyer flask, we have this yellow liquid. That yellow liquid is being poured through this filtration device. It has a piece of filter paper. You see the white paper in there. There's a piece of filter paper, and it looks like a funnel. You're pouring that yellow solution in, and what remains on the filter paper after all the liquid is seeped through, the beaker collects the liquid, and the filter paper collects the solid. Filtration is a physical technique to separate types of matter. If you separate a solid from a liquid, you know without a doubt that you have a mixture. Distillation is another type of separation technique. You saw this at the beginning of class during the demonstration. Distillation uses differences in boiling points of substances. Boiling point is the temperature at which a substance evaporates from the liquid state to the gaseous state. We know that water and salt have two different boiling points. Water boils at 100 degrees Celsius and salt boils at approximately 1,413 degrees Celsius. So if we blend these two substances together, water and salt, or sodium chloride, the chemical name for salt, if we blend them together in a container, we would call them a homogeneous mixture. Homogeneous because it looks like it's one pure substance upon observation. I don't see little specks of salt, or I don't see differences in states of matter. Homogeneous mixture. So if I were to take this homogeneous mixture of water and salt, and if I were to place it on a Bunsen burner or an open flame or even a hot plate, and I were to set the temperature to high, 100 degrees Celsius, eventually all of the water in that sample is going to evaporate, but the salt is going to remain in that container. There's no way that we could reach 1,413 degrees Celsius using a hot plate or a Bunsen burner, so my salt is going to remain in the container. This is a process called distillation. So I'm using the differences in their boiling points. So water boils at 100 degrees Celsius, whereas salt boils at 1,413 degrees Celsius. And because there's such a big difference between those boiling points, we can easily separate them by boiling this substance out first. And that would leave the second substance, which has a much higher boiling point, left in my container. And that's exactly what's happening over here in this distillation setup. We have a sample of salt water here, on this volumetric flask, or in this distilling flask. We have a Bunsen burner underneath that's shooting up hot flames. As this solution starts to boil, that water is going to evaporate. The water is vaporizing. But here, notice how it has a stopper on the top, so that evaporated water, the water vapor, doesn't have anywhere to go. It can't evaporate into the air. It gets trapped. So that evaporated air, gases expand and they move in rapid random motion. So those gaseous water vapor molecules are going to continue down this condensing tube. In this condenser, we have cold water that's moving in and out. So you see these arrows. These tubes would be connected to a water source. We have cold water circulating throughout this condenser. So when cold temperatures hit the water vapor, they condense. My water goes from the gaseous phase back to the liquid phase because of the change in temperature. And because it's on this downward slope, that water gets collected in this receiving flask down here at the bottom. So I have pure water in this receiving flask. And the salt remains over here in this distilling flask as a solid. So is distillation considered a physical separation or a chemical separation? When water goes from the liquid to the gaseous state, do its properties change? A change in states of matter from solid to liquid to gas or anywhere in between is a physical change. Water is still vapor regardless if it's a solid, a liquid, or a gas. It retains all of the same properties. Same with the salt. All we've done is physically separate them using that difference in boiling point. The second type of separation technique that we'll talk about is called chromatography. This technique separates substances on the basis of differences in solubility. Some substances dissolve a little bit better than others. We have a mobile phase, mobile meaning it moves, and we have a stationary phase. Stationary, it stays put. So I'm just going to put stays there. How does chromatography work? And we're going to do a lab similar to this a little bit further towards the end of the year. But what we have here on this piece of chromatography paper, it's just a very thin paper, is a dot of ink. That dot of ink, although it looks black, it's a mixture of many different colors. So we put the tip of this filter paper into some water. Water is known as a universal solvent. It can easily dissolve many types of substances. Water is the mobile phase. Water travels up this filter paper or this chromatography paper, just like it does when it rains outside and the back of your jeans or your pants get wet. That water travels up and it gets the back of your pants wet. Not just the very bottom, but it travels up and makes a wet mess. So water travels up this chromatography paper much the same way, and once it hits this dot of ink, which that dot of ink is a solid and our water is a liquid, once that water hits that dot of ink, it starts to carry that ink. Now, there are different colors within that ink. Different colors dissolve different ways, and it has to do with their mass and how heavy they are. So if you consider a backpack, if you're walking down the hall, a very light backpack is easy to carry, and you can carry it very long distances. But if you have a backpack that's filled with 5 chemistry books, it's very heavy, you won't be able to carry it very far. So you can see that the colors are starting to separate here. And then at the end, you can kind of see this little line here. That's where the water has traveled and stopped on this piece of filter paper. And you can see that you've got purple on the bottom. It looks like yellow, then green, and then blue at the very top. So what this has done is it has separated that ink into its respective colors. I can tell you that purple is the heaviest color and blue is the lightest color. And I know that because blue traveled the furthest up that filter paper, so as water was carrying these colors, it started to drop them off once they were too heavy to carry any further. So that means the purple was the heaviest and the blue was the lightest. Chromatography is an example of a physical separation technique because all we've done is take the original mixture and we've separated it into its component parts. It didn't change, it's not different than it was before. A chemical reaction didn't occur, it's just been separated into its component parts. Think of it kind of as, say, a salad. And a salad, if I were to separate it into its component parts, the lettuce first, then the tomatoes, then the cucumbers, then the carrots, if I've separated them out and kind of grouped them by category, the substances actually remain the same. Lettuce didn't change from one substance to another. I've simply removed it into different components. That way they're all together. The last separation technique that we have is called electrolysis. Electro meaning electricity and lysis to break. So we're using electricity to break apart a molecule or a compound. It's a chemical means to separate a compound into its part. It brings about a chemical change. Because it brings about a chemical change, electrolysis is a chemical separation. Let's go back to that trusty water molecule that we're all familiar with. 1 oxygen and 2 hydrogen atoms are chemically combined to form a water molecule. We can use electrolysis to chemically separate or break these bonds in between the hydrogen and oxygen. As a result, when I do break them apart, I end up with hydrogen gas and oxygen gas, O2. Recall that the properties of hydrogen gas and oxygen gas are very different than the properties of this water molecule that we started with over here on the left-hand side. So in electrolysis, if we look at the picture, we have electricity here in the form of a battery. We have a cathode and an anode. The electricity from the battery supplies the energy needed to break these bonds here in between the hydrogen and the oxygen and form new bonds in the hydrogen molecule and oxygen molecule, which are my products. Now here's the most important part of today's lesson. How can we classify matter? We're going to look at the following 3 traits in order to take any type of matter and classify it as either a pure substance or a mixture. The first trait we'll consider is appearance. When I look at this sample of matter, does it look consistent or the same throughout, or can I see differences in that sample of matter? The second trait I'm going to look at is bonding. Can my sample be separated physically, or does it require a chemical reaction? And the last trait I'll look at is composition. Does this substance have a definite or indefinite ratio of elements, molecules, and compounds? Composition tends to be the trickiest trait out of the 3, so let me give you a quick example using our trusty water molecule. Water has a definite composition of H2O, always 2 hydrogen to 1 oxygen. It doesn't matter if I take the sample of water from my sink at home, from the sink at school, or if I take a sample of water from the nearest river nearby. A water molecule is always 2 hydrogen to 1 oxygen. An indefinite ratio means when I take a sample, the ratio of one substance to another changes. Let's use salt water as our example of an indefinite ratio of elements to molecules to compounds. Salt water is a combination of salt particles, sodium chloride, and water molecules, H2O. Now they're not chemically combined, they're just hanging out in the same container together. An indefinite ratio is the number of salt particles to the number of water particles. If I make this sample, there may be 3 salt particles to every 5 water particles. But if somebody else makes a sample, it may be 2 salt particles to every 10 water particles. Another example would be if I take a sample of ocean water. Let's say I go to Galveston and I take a sample of ocean water. The number of salt particles to water particles may be, let's make up a number, 7 to 15. Let's say later on in the day it rains, it pours. If I take another sample of that water from Galveston, now there's more water particles than there were before because of the rain. The rainwater has been added to the ocean water. So now the number of salt particles remains the same, 7. but the number of water particles is increased because of the rain. Let's call that 20, and that means I have an indefinite ratio, that the ratio of one element or substance to another changes depending on the sample that you take. In order to simplify classifying matter, we're going to create a flowchart that will help us go through those 3 traits on the previous slide: appearance, bonding, and composition, to help us determine if that sample of matter is a pure substance or a mixture. I would recommend starting on a brand new sheet of paper or on the back of your notes if there's nothing written there, and turn your paper sideways so that it's in the landscape orientation. You're going to start by putting this little word matter at the top of your paper. The very top. I can't write that small, so I'm just going to put an M there for matter. Remember that matter is anything that has mass and volume. Next step. Off of the box at the top of your paper that says matter, I want you to draw an arrow going down. And inside a new box, I want you to write, is it uniform throughout? Is it uniform throughout? This question helps us determine the appearance of our sample of matter. Does it look the same throughout, or can I see differences throughout my sample? If the answer is no, it does not look uniform throughout, I can see differences throughout my sample of matter, then this was easy. I have a heterogeneous mixture on my hands. Draw your arrow with no on top and heterogeneous mixture as your answer choice. But if the answer was yes, my sample of matter looks the same or uniform throughout, then I want you to put the word homogeneous under the yes arrow. But a homogeneous substance can be a mixture, or it can be a pure substance. Pure substances are going to look the same throughout, just like a homogeneous mixture looks the same throughout. So we need to ask an additional question. Off of the homogeneous box, I want you to draw another arrow pointing down with the second question. Does it have variable composition? Does it have variable composition? Remember that composition refers to what makes up that substance. If it has variable composition, it means every time I take a sample of matter, the ratio of one substance to another substance changes. If the answer is yes, my substance has variable composition, then I have a homogeneous mixture on my hands. This was that salt water example that I gave you. The ratio of salt to water particles will vary for every single sample that I take. Because it has variable composition, it means I have a mixture. But if my substance has definite composition and the answer to our question is no, that means we have a pure substance. Pure substances do not vary in composition. Recall that a pure substance, like water, always has a definite ratio of 2 hydrogen atoms to 1 oxygen atom. We still have one more problem. So off of this no arrow, you have pure substance. There are several types of pure substances. We have to differentiate between them. The last question I want you to ask is, can it be separated into simpler substances? Can it be separated into simpler substances? In other words, are there chemical bonds holding 2 different atoms together, or are these atoms free-floating all on their own? If the answer is no, my substance cannot be separated into simpler substance, the answer is element. Recall that element is the simplest form of matter that cannot be broken down further. Examples of elements, choose any from the periodic table. Carbon, phosphorus, potassium, manganese, any element off of the periodic table is the simplest substance, pure substance that I can have. And the very last part of your flowchart, if I can separate my pure substance into simpler substances, then I have a compound. So if I have something like that water molecule, H2O, Can I break down H2O into simpler substances? I can. There are chemical bonds holding the hydrogen to the oxygen atom. If I can break those bonds, I'll get simpler substances like hydrogen and oxygen. So that means I have a compound. We're going to use this chart to help us classify any type of matter. I should be able to give you any sample, and through your line of questioning, you should be able to tell me A, if you have a pure substance or a mixture, and B, if you have a mixture, you should be able to tell me if it's heterogeneous or homogeneous, and if it's a pure substance, I want you to be able to tell me if it's an element or compound. Ensure that you have this chart copied down exactly in your notebook. We're going to use it in the future.